Moving on to the difficult part of the unit for organic chemistry. Actually, it is not the difficult part, it is the trickiest part actually. The part where you will have to memorize a lot of things, you will have to memorize a lot of reactions in order to score high on your exam. Okay. So the first part will start with aldehydes and ketones. These are the two things that you have seen previously in my video, but I didn't teach you anything in detail. So now here we will learn them in detail about the aldehydes and ketones. Okay, we will learn them in detail about the aldehydes and ketones. The actual configuration of aldehydes are like this. The carbon will be bonded with oxygen, the double bond, and it will also be bonded with an hydrogen as well. This is the configuration of aldehyde. And for ketone, it will be similar, whereas it will be like this only. It will be like this. The ketone will be like this. Okay, and the other carbon will be attached with two R groups or alkyl groups or methyl groups. Okay. In the aldehyde, the carbon can be attached with one hydrogen, but here the carbon will not be attached with any hydrogens. It will be attached with either alkyl or aryl groups, but no hydrogen. This is the main difference between aldehydes and ketones. Aldehyde, the carbon atom in the aldehyde, the carbon atom which is bonded with the oxygen, which is double bonded with oxygen, which can be attached with only one hydrogen. Whereas in ketone, the carbon atom which is double bonded with the oxygen cannot be attached with any hydrogen. This is the main difference between aldehydes and ketones. So which makes the structural formula as CHO for aldehydes and only CO for the ketones. Okay, this is the main difference between aldehydes and ketones. And we're actually starting the carbonyl compounds. Both aldehydes and ketones are known as the carbonyl compounds. Both aldehydes and ketones are known as the carbonyl compounds. Alright, so if there is only one carbon atom, we say them as methanol. If there is two carbon atoms, we say them as ethanol. As the name suggests, the number of carbon atoms, we add Al with it. For let's say this one, 4 carbon atoms, we say them as butanol. And here in the ketone, one, if there is a, let's say here you can see there is 3 carbon atoms, so we can send them as propanon, 4 carbon atoms butanon, and this is pent-10-2-on. If you guys want, I can show you some examples here. Here it is pn-10-2-1. Why it is pent-10-2-1? Because in the straight chain you can see 1 2 3 4 and 5. There are 5 carbon atoms, and the C double O group is in the second carbon atom. That is why we have regarded them as pent-10-2-on. Okay, and for pent-10-3-on, the carbon is in the third carbon atom. The carbon oxygen double bond is in the third carbon atom. That's why it's 3-on. And regarding 3-butyl-2-on, you can see in the straight chain there is only 4 carbon atom. That's why we have signed it as butane. And the second carbon atom, there is the CO group. This CO group is in the second carbon atom. That's why we have said as 2-on, butane 2-on. And this 3-methyl has come from here because the CH3-methyl group is in the third carbon atom. And here we have taken one particular thing, which is we have started the carbon counting from here rather than here, and we have taken these aldehydes counting first, then this methyl counting. If we have taken this methyl counting first, then it would have been 2-methyl butane 3-on, but we didn't take it as 2-methyl. Let's say this is 1, this is 1, this is 2, this is 2-methyl, right? And this is 3 ketone. The ketone 1 would have been, this one would have been 3, but no, we have taken it according to the priority group because ketones are in high priority group than the methyl groups. That's why we have taken ketones as first. So this carbon is first, this carbon is second, this carbon is third, this carbon is fourth, and this carbon is fifth. This is how we have taken butane 2-on and 3-methyl. Okay, hopefully you guys have understood this small simple part. Now moving on to the next page. We will learn about the reaction with hydrogen cyanide. Okay, we will learn after the reactions with hydrogen cyanide. So what is the reactions of hydrogen cyanide? Who will actually react with the hydrogen cyanides? The carbonyl compounds will react with the hydrogen cyanides. So here you can see propanol. This is a propanol which will react with the hydrogen cyanide. The propanol will react with the hydrogen cyanide. So when the propanol reacts with hydrogen cyanide, if actually we draw them down, let's say we are only drawing this part. This is CH and this is C double O plus the HCN. This is the CH3CH2 plus HCN. It becomes this C breaks this double bond and it becomes OH, because this H comes and attracts with and bonds with this O, so it becomes OH. Okay, this particular H remains, it is remaining right here, and this CN as well will come and bond with this carbon. Okay, and this CH3CH2 will remain just like it. This is how it happens, how the HCN reacts. The out of the HCN, the H goes and reacts with the oxygen, and the CN as a whole come and bonds with the carbon. This is how it becomes like this. Okay, this is how it becomes like this. Now moving on, this is also the reaction of addition of butanol. In the butanol, actually the same thing happens, that this hydrogen goes and bonds with this oxygen, and this CN interacts with this carbon atom, which is double bonded with the oxygen. Okay, this is how they actually work. And now how we will actually name this one. The terms of naming this one is, we know this is our first carbon atom, this is our second carbon atom, this is our third carbon atom, and this is our fourth carbon atom. So this OH group is in the second carbon atom, so we'll write it down as 2-hydroxy, and as there is 4 carbon atoms, we can say 2-hydroxy butanitrile. And for the butanol one, it will be the same. In order to name them, it will be 2-hydroxy 2-methyl butanitrile. So this is actually how we will name them, and this is the reaction of the carbonyl compounds with the hydrogen cyanide, something that is really important to understand. Okay, something that is really important to understand. Now for this carbon atom is bonded with this hydrogen, like this hydroxyl group as well as this CN. Okay, so if we count from here, this is first carbon atom, this is second carbon atom. So this second carbon atom is bonded with the hydroxyl group, that's why I have written 2-hydroxy. And this carbon atom is also bonded with these 2 methyl groups. Okay, that is why we have written it 2-hydroxy 2-methyl butanitrile. If I actually draw them down as well, if I actually draw this down as well, just give me an example. Let's draw this first. It will be C double O, and then it will be sorry, my bad. It will be C double O, then it will be, sorry, my bad, it will be CH3, another CH3, and here will be another CH2. So basically this is how it is bonded, right? Sorry, this is not like that actually. This is CH2, and here it is the CH3. So basically this is how it is bonded. Now when you will add this hydrogen cyanide, it will become like this. It will become, this O will be replaced by another H, and the double bond will become single bond, so it will become COH, and this CH3 will remain just like it is, and this CN will come and go right here, so it will become with CN, and another one is this CH2 CH3. Okay, both of them are actually bonded together, both of them are in the same chain actually, so it is CH3. Now we know this is our first carbon atom, this is our second carbon atom. As this OH group is in the second carbon atom, we can say 2-hydroxy. Okay, 2-hydroxy. And There is, we have written 2 methyl. Why 2 methyl? Because in the second carbon atom there is one methyl group, which is CH2. Okay, CH2. So that is why we have written it down as this is the third carbon atom. If this is the first carbon atom, this is the second carbon atom, this is the third carbon atom, this is the fourth carbon atom, and in the second carbon atom there is also another methyl group, which is CH3. So it has become 2 hydroxy 2 methyl 1 2 3 4 butane nitrile. This is how it is, 2 hydroxy 2 methyl butane nitrile. Hopefully you guys have understood this part in detail. If you have any question, you can ask me in the comment box. I will try to explain them again to you guys. Now moving on, we have previously learned about the SN1 SN2 mechanism, right? We have learned the SN1 mechanism in real detail. Now here in the nucleophilic addition mechanism, this is exactly the same one that we have seen previously as well, and you will have to understand and memorize these parts in real detail, because it is very important to remember them. It is very important to remember them actually. So now let's understand them. So basically we know here this carbon is positively charged and this oxygen is negatively charged. So basically what will happen is this Cn- nucleophile will be attacking this electropositive carbon atom from both the sides actually, though it has been showing from the left hand side, but it actually will be able to attack the electropositive carbon atom from the either sides, both the left hand side and left hand side, from the left hand side and the right hand side. So basically now here this Cn will be bonded with the Cn, and the double bond between the carbon and the oxygen will become single bond, and now this oxygen has 2 lone pairs of electrons. So now what will this oxygen will do is this oxygen will get attracted to the H plus hydrogen ion of the Cn, HCN. So now it will be attracted to the H plus of this HCN, and it will bring this H plus to itself, and it will become OH, and now the Cn minus is alone. So this is basically the nucleophilic addition mechanism, where this reaction involves the intermediate and a hydrogen cyanide molecule as well. Okay, and at the end it will only left with a Cn minus and this whole part. So this is exactly the same thing that we have seen in our SN1 mechanism, because the Cn minus nucleophile can attack from either sides. So this is what we have written. At the end of the reaction, the product mixture shows no optical activity because the Cn minus nucleophile can attack from both the sides with equal probability, and if they can attack with the same probability, it will form a racemic mixture. So there is no optical activity. This is something that we have seen previously as well, right? This is because the carbonyl compound is planar around the carbon oxygen bond, double bond. The electropositive carbon and the carbon oxygen double bond can be attacked by Cn minus nucleophile from either side with equal probability, leading to the formation of a racemic mixture. Just the thing that I have made you guys understand previously. Hopefully you have understood it completely. Now moving on to the some of the extra important parts of this chapter, which will determine the rate of reaction. Okay, there is something called the rate of reaction and the sodium hydroxide, potassium hydroxide neutralization of this mechanism. We will just learn them right now. So let's start. Alright, so now we will go after the factors which will increase the rate of reaction. Now let's say if we add cyanide salts, let's say if we have added KCN or NaCN, what will happen is this, if you add KCN to here, so the CN minus the concentration of this CN will increase, right? The concentration of the CN minus will increase. So if the concentration increases and it is a reversible reaction, what will happen is now the reactants has become greater. This is the reactant part, right? The reactant has become greater. So the equilibrium shifts will to the right. So now the equilibrium will shift to the right. So now the product will increase and the product formation will increase. If you add cyanide salts, that means there are more reactant, and at that time the equilibrium will shift to the right, which will lead to the formation of more and more products. So basically this will speed up the reaction as well, because if there is more concentration of reactant, we know as the concentration of the reactant increases, the rate of the reaction increases, right? This is how this is. As the concentration of the reactant has increased, the rate of the reaction will increase, because more and more cyanide salts will react with this one. So basically this will increase the rate of the reaction. Okay. Now moving on here, if I add a small amount of alkali or sodium hydroxide, let's see if I've added some sodium hydroxide right here. This OH minus of this sodium hydroxide will neutralize this H plus, right? Will neutralize this H plus. If the H plus is neutralized, we can write it down as HCN becomes like this, H plus and Cn minus, right? This is the reaction of HCN, right? H plus and Cn minus. If you add sodium hydroxide, then this H plus gets cancelled out. So when there is a lesser amount of H plus, then this HCN starts converting into Cn minus more to make them both of them equal. Now as H plus has been neutralized by the sodium hydroxide, this part has decreased. So now HCN will start forming into this part. The equilibrium will shift to the right to make sure the Cn minus increases. So now the Cn minus will increase. So if the Cn minus increases, it will also lead to the formation of more and more products, and it will also speed up the reaction. This is something that we have to understand. Okay, this is the thing that they have written right here as well. So please go through it and try to understand. If you don't understand, let me know. I will make understand again in the comment box. The hydrolysis of nitrile and the hydrolysis of cyanohydrin. So nitriles, we will actually hydrolyze nitrile. To hydrolyze nitrile and hydrolyze cyanohydrin, the reagents that are required is dilute HCl or any strong acid for both of them, and the condition will be heat under reflux. In both the hydrolysis, you will need a condition of heat under reflux, and the organic product that will form will be carboxylic acid. Now let's understand this. Here, this is propane nitrile with which we will hydrolyze with water in the presence of acid, which will form propanoic acid and NH4 plus. As there was H plus present, that's why it has formed NH4 plus. If it wasn't present in the form, if the reaction wasn't carried out in the presence of acid, then it would have formed NH3. Now here we will do the hydrolysis of cyanohydrin. So this is the cyanohydrin, which is 1, 2, 3. So this is actually 2-hydroxy propan nitrile. This is 2-hydroxy propan nitrile with which we will hydrolyze. So when we hydrolyze it, it will form 2-hydroxy propanoic acid and ammonia. As it wasn't carried out in the presence of acid, that's why it has formed NH3. If it was carried out in the presence of acid, any strong acid, it would have formed NH4 plus. So basically this is the hydrolysis of nitrile and the hydrolysis of cyanohydrin. So you guys will have to memorize this 3 point and try to remember this this equation as well, and how the things are carried out. Please try to remember them because this is very important. The equations are very important. These equations are very important. Now we'll look after the reactions of the carbonyl compounds. Okay, we have come across the reactions of carbonyl compounds, which is actually the main part of unit for organic chemistry, the reactions. We have now we have entered into the reaction part, where we will learn about the reactions of carbonyl compounds. There are reduction and oxidation of carbonyl compounds, and there will be also carboxylic acid reactions, ester reactions, and acyl chlorides reactions. So all of those things, we'll learn them in detail. So now the first reaction of carbonyl compounds is with Brady's reagent. This is Brady's reagent. So why do we actually carry out this reaction? We actually carry out this reaction in order to figure out, let's say you have got a carbonyl compound. Okay, you have got a carbonyl compound, but you don't know whether it is aldehyde or ketone, because aldehyde and ketone both are known as carbonyl compounds. So to figure out whether it is a carbonyl, whether it is a aldehyde or ketone, we react the carbonyl compound with the Brady's reagent, which means 2,4-dinitrophenylhydrazine, which means 2,4-dinitrophenylhydrazine. So basically this is the 2,4-dinitrophenylhydrazine. This is the 2,4-dinitrophenylhydrazine. So we will react this. We will react a carbonyl compound. This is the carbonyl compound with 2,4-dinitrophenylhydrazine, and we will try to figure out whether it is an aldehyde or ketone. So the reagents that are required is the 2,4-dinitrophenylhydrazine solution, and it will form yellow or orange crystalline precipitate. After the reaction, yellow or orange precipitate will form. So how we will carry out the test? We will take 3 centimeter cube of 2,4-dinitrophenyl hydrogen solution in a dry test tube, and then we will add a few drops of a carbonyl compound. Yellow or orange crystalline precipitate will form. If yellow or orange crystalline precipitate forms, that it confirms that it is a carbonyl compound. Okay, when a carbonyl compound reacts with Brazil reagent, it forms a yellow or orange crystalline precipitate, indicating the presence of a carbonyl group. So basically, this is how we will figure out whether it is a carbonyl compound or it is anything else. Let's say whether it is alkane or a carbonyl compound, or let's say whether it is anything else. And how we will actually figure out whether it is aldehyde or ketone, this is something that we will learn in the later part. Okay, how to distinguish between aldehydes and ketones. But for now, we will carry out reaction with 2,4-dinitrophenyl hydrogen to figure out whether it is a carbonyl compound or not, or it is a ester or acyl chloride or carboxylic acid. This is how we will figure out. So identity of the carbonyl compound. How we will identify the carbonyl compound? First of all, react the carbonyl compound with a solution of 2,4-dinitrophenyl hydrogen. Then we will filter off the precipitate that forms. There will be a precipitate that will form, right? The yellow orange crystalline precipitate. We will filter off that particular precipitate. And after filtering off, we will recrystallize that precipitate. After recrystallizing, we will dry the purified product and measure its melting temperature. We will measure its melting temperature. And we will compare this melting temperature with the melting temperature of 2,4-dinitrophenyl hydrogen derivatives of aldehyde and ketone. Okay. We will then compare with the 2,4-dinitrophenyl hydrogen aldehyde and ketone derivative. Let's say if it is pentanol, its melting temperature will be 104. Now if you have when after carrying out after measuring the melting temperature, if you see that it is 156, then you can say yes, it is pentan 3-on and it is ketone, it is not an aldehyde. So this is how you will actually figure out whether it is an aldehyde or ketone. This comparison will help identify the carbonyl compound. This method allows for the identification of the carbonyl compound by comparing the melting temperature derivatives with known values. So you are comparing with the known values to figure out whether it is actually a carbonyl compound or not. And if it is a carbonyl compound, you can also figure out whether it is which one it is. So this is a very easy way, right? So basically the main reason behind carrying out this is to figure out whether it is actually a carbonyl compound or anything else. Let's say it is an ester, it is an acyl chloride or aldehyde or ketone. So if it is aldehyde or ketone, its melting temperature will be in the range with the derivative values that we actually know, that we can actually figure out from the data booklet. Okay, not in your copy actually, not in your exam, but in the real life data booklet. Okay, so now we are done with that part as well. Now moving on, we will try to figure out that how we will be able to distinguish between aldehydes and ketones. We will try to distinguish between the aldehydes and ketones. Let's say you have figured out, yes, it is a carbonyl compound, it is not an ester or acyl chloride. Now the next step is to figure out which carbonyl compound it is, whether it is an aldehyde or ketone. So to figure out whether it is an aldehyde or ketone, we will have to carry out a lot of things. The first thing we can do is doing an oxidation reaction. So how does the oxidation reactions are carried out? Ketones are actually very difficult to oxidize. You cannot oxidize ketone. So ketones cannot be oxidized. Only aldehydes will be oxidized. So what we will do is we'll add potassium dichromate 6 to that particular compound. If it turns orange or green solution, if it turns from orange to green solution, that means it is an aldehyde. If there is no color change, then we can say yes. If it remains orange, it doesn't change into green, then we can say it is an ketone. Okay, this is how we will distinguish between aldehyde and ketone. First we have to figure out whether it is actually a carbonyl compound using it with 2,4-dinitrophenyl hydrogen. And if we are confirmed that yes, it is 100% a carbonyl compound, now we have to distinguish whether it is an aldehyde or ketone. To distinguish, we will pass it through acid potassium dichromate 6. Potassium dichromate 6 will be poured into it. So after pouring acidified potassium dichromate 6, if the color changes from orange to the green solution, it is an aldehyde. If it doesn't, if that color remains the same, then it is a ketone. Okay, because ketone cannot be oxidized, only aldehydes can be oxidized. Now moving on, we will look after the tolerance test. Tolerance test is a very important test. So what are the things that are required to carry out the tolerance test? Now let's understand this tolerance. So the chemicals required, the first chemical that is required is this silver nitrate is required, sodium hydroxide is required, and dilute ammonia is required. Okay, these are the three things that is required to carry out tolerance test. Tolerance test is just another test which will distinguish whether it is an aldehyde or a ketone. So how do we actually carry out the reaction? We know the chemicals that are required, which is silver nitrate, sodium hydroxide, and dilute ammonia. So the first, to carry out the tolerance test, we have to prepare the tolerance reagent. We'll have to prepare this tolerance reagent. So to prepare this tolerance reagent, we will take 10 centimeter cube of 0.1 mole per dm cube of silver nitrate solution in a test tube, and then we will add few drops of 2 mole per dm cube of sodium hydroxide. Okay, when you have added both of them, the silver nitrate and the sodium hydroxide, this results in the formation of a brown precipitate of silver hydroxide. Okay, this results in the formation of a brown precipitate of silver hydroxide. Now, this silver hydroxide is actually unstable. As it is unstable, it will decompose, and it will decompose into Ag2O, which is silver 1 oxide, a dark precipitate. As this AgOH, which has been formed by the reaction of the chemicals of silver nitrate and sodium hydroxide, it is unstable and it will very soon decompose and it will become Ag2O, which is silver 1 oxide, and the silver 1 oxide is a dark precipitate. And what we will do is we will allow, let's say this is the uh, container in which, or let's say this is the test tube at which the reaction was carrying out. So now this Ag2O has has formed. So when this Ag2O has formed, there is also water as well. So what we'll do is this Ag2O will be a precipitate. So what we'll do is we will let this precipitate to settle at the bottom of the test tube, and this water portion will be discarded from the top by decanting. Decanting means, let's say the precipitates are at the top and the water portion is at the upper position. So we will use another third party in order to remove this water from the test tube. And after removing that, we will add aqueous ammonia solution. This is the aqueous ammonia solution to the precipitate. To this precipitate, we will add that aqueous ammonia solution, and then we will shake this mixture until all of this precipitate dissolves, or the solid dissolves, and forms a colorless solution. This colorless solution is actually the tolerance reagent, and this is the actual reaction. This Ag2O was reacted with this ammonium solution, and there was some water left, right? After decanting, you cannot decant all the waters, there will be still a little bit of water, and then later on it is the thing that will actually form. This is what the tolerance reagent is, and the name of this one is diamine silver 1 ion, or you can also say alkaline ammonical silver nitrate solution, which is actually the tolerance reagent. You will have to memorize these two names. You can memorize actually either of them or any one of them. This is very important to remember, and you have to understand this equation as well. Try to memorize this equation and try to remember this particular equation and the name of it. Okay, the formula and the name of it. Now we have prepared the tolerance reagent. Now it's time to do the tolerance test. We have prepared tolerance reagent. Now let's apply the tolerance test. Okay, so to carry out the tolerance test, first of all, what we will have to do is we will take 5 centimeter cube of tolerance reagent that we have prepared previously, and onto the tolerance reagent we will actually put the tolerance reagent in a test tube, and then we will add few drops of the carbonyl compound which we are going to oxidize. Okay, so the first thing that I want to understand you guys is that this tolerance test is also an oxidation. Okay, so and we have also said previously that ketones do not get oxidized, so please remember that particular thing as well. So after adding the carbonyl compound to the tolerance reagent in a test tube, we will warm the mixture in a hot water bath. So we will observe that with aldehydes, a silver mirror on the lower part of the test tube will form. Silver mirrors will form on the lower part of the test tube. But as we have previously also said that ketones never get oxidized, so there will be no change with the ketones. So if we see silver mirror forming, we can say it is an aldehyde. If there is no change, then we can also say it is a ketone. So this is how we will distinguish between aldehydes and ketones. This is the actual reaction which we have to remember. First of all, this part, this formula of the tolerance reagent is important. Now, the aldehyde reduces tolerance reagent to metallic silver, okay, which is this 2Ag. The aldehyde reduces to the tolerance reagent to this metallic silver, which forms the silver mirror. The aldehyde itself is oxidized to carboxylic. Actually, this is not a carboxylic acid, this is carboxylic salt, okay. It will form a carboxylic salt. Why it will form a carboxylic acid salt? Because we will explain them in detail later on. Just give me 1 minute. The tolerance reaction occurs in an alkaline medium. As it occurs in alkaline medium, the formed it will actually form the carboxylic acid. But as the reaction is taking place in an alkaline medium, this carboxylic acid will form with the OH minus of the alkaline medium, and it will become RCOO minus. Okay, so it will become RCOO minus. This is the reason. And in the reaction, this carbonyl compounds is forming this RCOO minus, which is the carboxylic salt. Okay, it is forming the carboxylic salt. Why? Because it is carried out in alkaline medium where the carboxylic acid which should have formed reacts with the OH minus of the alkaline medium and becomes a carboxylic salt. This is the main reason. Now the 2 points that we have to understand is this aldehydes is becoming carboxylic salt and the tolerance reagent is oxidized, sorry, the aldehyde reduced this tolerance reagent into this silver mirror, which is 2Ag, okay, which is Ag solid, which forms the silver mirror actually at the lower part of the test tube. And as this aldehyde has reduced this tolerance reagent, we can say aldehyde is an oxidizing agent right here. So basically this is the main thing, and ketones do not go on oxidation, so they do not reduce tolerance reagent, and they as they do not get oxidation, we have also said this before as well, right? Ketones can never be oxidized. The another oxidation reaction that we have to understand for the carbonyl compounds is the Fleming's test. In the Fleming's test, we will have to first prepare the Fleming's solution, just like the way we prepared tolerance reagent. We'll prepare Fleming solution. So how we will actually prepare the Fleming solution? Fleming solution will be prepared by mixing equal volumes of Fleming solution A and Fleming solution B. So what does actually Fleming solution A contain? Fleming solution A actually contain aqueous copper to sulfate, and Fleming solution B contains sodium hydroxide and aqueous sodium potassium tartrate solution. So in order to create the Fleming solution, we will actually mix this aqueous copper to sulfate with sodium hydroxide and aqueous potassium sodium tartrate solution. When we will mix these 3 parts, Fleming solution will be formed, and then we will use that Fleming solution to carry out the Fleming's test, which is the oxidation of aldehydes. Now take this Fleming solution in a test tube. The procedure is we will take this Fleming solution in a test tube. The second thing that we will do is we will add 0.5 cm cube of carbonyl compound, either an aldehyde or ketone, any of them, and then we will warm the mixture in a hot water bath, which is exactly the same as the tolerance reagent, right? Then for aldehyde, what we will observe is we will observe a red precipitate of copper 1 oxide is formed. A red precipitate of copper 1 oxide will form. A red precipitate of copper 1 oxide will form, and this is actually the reaction mechanism. This is Cu2 plus, this is 5OH minus, this is Cu2O, and another one is this is RCO minus, and this is water. So it will actually form a red precipitate. The formation of red precipitate, this is something that you will have to memorize for the Fleming's test. And here you will also have to memorize about the silver mirror that forms. These are the 3 lines that you will have to memorize for the tolerance reagent. You don't need to know about the reaction as a whole. These reactions never comes in the exam. The thing that comes is the colors that you will have to remember. And the red precipitate confirms that the presence of an aldehyde. And for ketones, there will be no visible change because ketones are never oxidized, and Fleming's test is an oxidation reaction. This indicates that ketone do not react with the Fleming's solution. So basically, we are done with the tolerance reagent and the Fleming's test as well. Now here comes the most important part, which is the iodoform test. This is a super important part, because iodoform test can be carried out with both the alcohols and the carbonyl compounds. So the first thing that we can see here in the iodoform test is carbonyl compounds containing the CH3CO groups gives a positive iodoform test. So this is an important part. I'll make you understand this simple part in detail. Just give me 1 minute. You will understand them in detail. CH3CO. So that means the carbon atom will be bonded, double bonded with oxygen, and there it will have a methyl group with it. So basically, iodoform test means the carbonyl compounds which have this configuration will only give positive iodoform test. That means this particular carbon will have to have a double bond with the oxygen atom and a methyl group. If this methyl group is not CH3 and CH2, then it will not give a positive iodoform test. So this is the main thing that you will have to possess in order to give positive iodoform test. I know it is a bit difficult to understand at first, but I will make you understand later on. Please give me 1 minute, I will make you understand this. So let's proceed towards the iodoform test. The reagents that are required is the iodine solution and sodium hydroxide solution. These are the two things that are required. Iodine solution and sodium hydroxide solutions are required to carry out the iodoform test. So let's carry out the test. Add a few drops of the carbonyl compound to 3 cm cube of this iodine solution in a test tube, followed by this sodium hydroxide solution. We will warm the mixture in water bath if required. Now what will be the observation? The observation will be a pale yellow precipitate with an antiseptic smell is found, indicating a positive result. So this is something that you guys will have to memorize. This yellow portion which I have written in yellow color, you'll have to memorize this observation, and you'll also have to memorize the reagents as well. And regarding the reaction, I'm writing down the reaction for you guys. Just give me 1 minute. The reaction will be just like this. The reaction will be like this, which is H3C COO. Here can be an hydrogen or an alkyl group plus 3 iodine plus 4 moles of sodium hydroxide is equals to CHI3. This CHI3 is very important because this is the iodoform which has been formed, plus plus 3 moles of water. So basically this is the reaction that actually carries down the reaction. Okay, this is the main reaction. Here you can see the requirement is followed, as this carbon atom is bonded with an alkyl group as well as a this carbon atom is bonded with a methyl group as well as a oxygen, double bonded with oxygen. If potassium iodide and um, NaClO are used as reagents, they react with each other to form iodine and alkali. Actually, this is not required for the time being. You can only stick with that particular part. This is an extra thing that I've given. You don't need to remember that actually. We can actually remove this part as well. We can actually remove this part. This is not important for the time being. Now moving on, here you can see that alcohols also give a positive iodoform. Okay, so the first thing that I have shown you guys about this CH3CHO part, right? About the ketones and aldehydes. Both the aldehydes and ketones actually reacts with gives positive iodoform test. Both the aldehydes and ketones gives positive iodoform test. Now let's understand which aldehyde and which ketones will not give positive iodoform test. Which ketones and which aldehydes will not give positive iodoform test. Let's say propanol. If we take propanol, only ethanol is the only aldehyde that gives positive iodoform test. Propanol doesn't give positive iodoform test. Why doesn't it give positive iodoform test? let's have a look at it. Let's draw the propanol right here. Okay, let's draw the propanol right here. So basically this is CO, this is H, and this is CH2, and this is CH3. So this is actually the propanol. Now you can see the carbon atom which is bonded with the oxygen is bonded with oxygen. Yes, that's true, but it is not bonded with CH3, it is bonded with CH2, but it should have been bonded with a CH3. That's why it doesn't give a positive iodoform test. Only ethanol is the only aldehyde that gives positive iodoform test. And in terms of ketones, if we look after the ketones, um, the ketone which have the CO bond, which have this CO bond in the second carbon atom only gives positive iodoform test. Let's say pentanthreone will not give positive iodoform test. Why doesn't pentanthreone gives positive iodoform test? If we draw pentanthreone, we can write it down like this. This is CO, and this is CH2, this is CH3, and this is CH2, and this is CH3. So this is actually pentanthreone, right? But as this C double O group is in the third carbon atom, it will not give a positive iodoform test. But butane 2 on would have given a pentane 2 on would have given a positive iodoform test. This is pentane 3 on, right? If this carbon oxygen bond was in the second carbon atom, it would have given a positive iodoform test. Basically for aldehydes, ethanol is the only aldehyde that gives positive iodoform test. And for ketones, to give positive iodoform test, the CO group should be in the second carbon atom, not in the third, fourth, or fifth. If this was in the second carbon atom and you replace this H2 with here, then it will give positive iodoform test. So basically, to give positive iodoform test for ketones, the CO group should be in the second carbon atom. I have written that particular thing right here, maybe. Yes. Ethanol, this will be ethanol actually. Ethanol is the only aldehyde that gives positive iodoform test, and ketones which has CO group on carbon number 2 gives a positive iodoform test. Now let's look after the alcohols. Alcohols also give a positive iodoform test, but there are some exceptions. Why exceptions? Only one type of alcohols give positive iodoform test. Okay. Alcohols means only the primary alcohol will give positive iodoform test. Sorry, the only primary alcohol that gives positive iodoform test is the ethanol. Ethanol is the only primary alcohol that gives positive iodoform test. And all secondary alcohols which have OH group on the second carbon atom will give a positive iodoform test. And tertiary alcohol never gives positive iodoform test. So the main criteria for alcohols to give positive iodoform test is they must have a structure like this: CH3, CH, and OH. So that means this a carbon atom should be bonded with both the methyl group and a hydroxyl group. The carbon atom should be bonded with one methyl group and one hydroxyl group. So in terms of the primary alcohol, only the ethanol is the only primary alcohol that is bonded like this with both the methyl group and the hydroxyl group. So it will give positive iodoform test. And in terms of secondary alcohol, if the second carbon atom, if the OH group is then the second carbon atom, then it is possible to create it like this. So it will give positive iodoform test. And tertiary alcohol can never form like this. So it will never ever give positive iodoform test. So basically this is the whole example of iodoform test. If you want more examples regarding each and every points, let's say for ketones, for aldehydes and alcohols, please comment down below. I will make a separate video for that particular thing about more examples of aldehydes which actually gives positive iodoform test and which doesn't. Same goes for ketones and alcohols as well. Now, moving forward, we will learn about the reduction of the carbonyl compounds. Up to now, we have seen about the oxidations, right? We have seen about the oxidations. The Fellings test and the tolerance reagent was the oxidations, as well as we have seen another oxidation where we added potassium dichromate 6 to the aldehyde, right? And the color changed from the green to the orange. Sorry, from the orange to the green. So these are the oxidations that we have seen. Now what we will do is we will learn about the reduction of the organyl, of the reaction of the carbonyl compounds. So to learn about the reduction of the carbonyl compound, just like before, we need a reducing agent. So here our reducing agent will be lithium tetrahydroaluminate or sodium tetrahydroborate. Lithium tetrahydroaluminate or sodium tetrahydroborate. So there are some exceptions in terms of using them. Lithium tetrahydroaluminate can be used in dry ether. What does actually dry ether means? Example is dry ethoxyethane. You can use it in dry ethoxyethane. You have to use them in dry ethoxyethane, because if you don't use it in dry condition or in dry ether, it will get hydrolyzed in water. If there is a small amount of water, it will get hydrolyzed. This lithium tetrahydroaluminate will get hydrolyzed with water. Okay, so you have to make sure that you are using it in dry ether, so that it doesn't get hydrolyzed in water, because getting it hydrolyzed in water um, actually diminishes the reaction procedure. Okay, it actually gets out of the way we want to carry out the reaction, because it forms something else that is required, because the reagent doesn't remain the way we want. The reagent forms into something else if we actually don't take in dry ether. Whereas sodium tetrahydroaluminate, which is another reducing agent, can be used in dry ether or in water. You can use it in both the ways. So when we actually reduce carbonyl compounds, what does actually form? You can see this is a propanol which has been reduced. Achha, there is one thing that I want to make you understand is, if this is this line, this is oxidizing agent. This is oxidizing agent, and if there is H in between a comma, this means reducing agent. Okay, this is the main this is the main difference between oxidizing agent and reducing agent. Now the reduction of butanone, which is ketones will be reduced to secondary alcohol, and aldehydes will be reduced to primary alcohols. When we reduce them, this is how they actually form. And at the end of the reaction, this product mixture must be hydrolyzed with dilute HCl to obtain the final organic product. To obtain the final organic product, you will have to hydrolyze this product with dilute HCl. This is something that you guys will have to carry out, or you will have to actually do. Now let's learn something more about mechanisms and everything. Okay. Now let's learn more about mechanisms. Now something more that I want to make you guys understand is this part. Okay, let's understand this part. Now, if I want to make you guys understand about that part, let's say LiAlH4. LiAlH4. Okay. This was the reducing agent, right? So basically, how does it carries out the reduction? We know this AlH4 as a whole is a nucleophile. This AlH4 is a source of H minus nucleophile. This is how it actually carries out the reduction. The main thing that I want to say is LiAlH4 is a source of H minus nucleophile. Okay, H minus nucleophile. And here we know there is a carbon oxygen double bond, right? So we can write it down like here. Carbon oxygen double bond. This is electropositive, this is electronegative. So this H minus nucleophile, what it does is, it will come right here like this, and it will attack the electropositive carbon atom, just like the way we have done the mechanism previously as well, right? So LiAlH4 is a source of H minus nucleophile. The CO oxygen is polar, and thus the electropositive carbon is attacked by this H minus. Okay, it will attack the H minus. This is how it is actually done. And when it attacks, it becomes like this. And here it bonds with the H. And now there is also H plus ions as well, right? There is also H plus ions as well. So there will be some H plus ions as well. And these oxygen with two lone pairs of electrons will attract, and as they have attacked, this will become like this. This carbon will be bonded with a hydrogen, and this O will be attached with this OH. So basically this is the configuration, or this is the structure that they will form. This is the structure of both these two parts. Okay, here you can see this carbon was bonded with hydrogen as well as this OH, and this carbon was also bonded with hydrogen as well as this OH. So basically this is how the mechanism works. So I have shown you an extra mechanism. I don't think this is important for your syllabus, but you can actually remember them because this is one mechanism that might come in your exam. So yeah, you can remember this mechanism as well, which is exactly the same as the SN1 SN2 mechanisms that we have seen previously. So yeah, now moving on to the physical properties of the carbonyl compounds. Now understanding the physical properties are really important. So the physical properties of carbonyl compound includes that carbonyl compounds never ever form hydrogen bonds between themselves. This is very important. They do not form hydrogen bonds between themselves. Doesn't mean that they do not form hydrogen bonds with others. Yes, they form hydrogen bonds with the others, but they never form hydrogen bonds between themselves. Okay. And the second property is there are permanent dipole forces as well as dispersion force between aldehydes and ketones. These two forces are really important to understand. Permanent dipole force, dispersion force, London force, and each and every force that you have learned in your AS chemistry. These are the forces that you guys will have to recall and revise for your Unit 4 and Unit 5 exam, because these two becomes really important to remember while solving the question papers, because in more or less every year there is a question regarding these forces. Now, even goes for aldehydes and ketone mixtures, there are permanent dipole forces and dispersion forces. Not only for aldehydes and ketones molecules, even for their mixtures, there are permanent dipole forces and dispersion forces that actually act. Now, the most important part is straight chain isomers can pack close together than branched chain isomers. Rather than branched chain isomers, straight chain isomers can pack close together. Okay. An example, force between branched chain isomers are weaker than that of straight chain isomers. So straight chain isomers have stronger forces between them than the branched chain isomers. These are the two lines that you have to understand. That straight chain isomers can pack close together, so they are more stronger. Okay, or the forces between them are more stronger, and branched chain isomers can pack less close together than the straight chain isomers. That's why they have weaker forces between themselves. For example, butane one has a melting point of this, and methyl propane has a melting point of this. So the straight chain isomer has a higher temperature, has a higher melting temperature than the methyl propane. Okay, the straight chain isomer has a higher melting temperature than the methyl propane, which shows that they are the forces between them are more stronger. The forces between them are more stronger, and they are more closely packed together. Now let's learn about the solubility of aldehydes and ketones in water. Now, aldehydes and ketones composed of small molecules such as methane, ethanol, propanol, and propanone are miscible in water in all proportions. So that means smaller molecules of aldehydes and ketones are miscible. That means they can mix with water in all proportions. So why are actually they able to mix? The reason for this solubility is that carbonyl compounds can form hydrogen bonds with water molecules. The same thing that I have make you understand before, that they do not form hydrogen bonds between themselves, but they can form hydrogen bonds with water molecules or anyone else. Even there, they are not form hydrogen bonds among themselves. So basically here you can say they have formed hydrogen bonds with the water molecule. This is the water molecule with which this CO has formed a bond. This CO, the electronegative oxygen and the electropositive hydrogen, has formed a bond between themselves. They have formed a bond between themselves. This is the bond. So basically the reason behind they being miscible with liquid is because they can form hydrogen bonds with water molecules. But the criteria is they have to be composed of small molecules. Let's say butanone will will not mix with water molecules. Propanone will mix because propanone is small molecules, butanol is not a small molecule. And the next point is hydrogen bonding between ethanol and water. This is the hydrogen bonding between ethanol water that I have shown actually in the drawing. Okay. The next part is the solubility of carbonyl compounds in water decreases with increasing the number of carbon atoms. The same thing that I have said. Propanone is miscible with water. Propanone is soluble, but as the carbon number changes and increases to butanone or heptanone or hexanone or sextone, what happens is the London force between the carbonyl molecules increases. That way they are less miscible with water rather than these small molecules of ethanol, propanol and propanol. Hopefully you guys have understood everything till now. After this we will move on to the carboxylic acids, which is way more important and which is very important for your syllabus. Esters and acyl chlorides as well.